In this session, we'll discuss the link between software architecture, DevOps, and testing. I'll discuss how architectural choices impact testing, enabling early defect detection, better coverage, and quicker software delivery. Let's begin with the basics. My name is Sarit Vakrat, and I have over 8 years of experience in managerial roles as QA and automation manager. I started as a manual QA, moved into automation development management, and today I lead an automation-only teams as a QA and automation manager at Glassbox. Outside of work, I'm also a Udemy instructor and a QA lecturer. Let's start with the story. In my first managerial role, I faced many challenges. I noticed production bugs creeping. We missed critical bugs, and our existing automation framework struggled to keep up with the new services. It got me thinking, was there a common thread here? I realized I had overlooked a crucial factor: our software architecture and its profound impact on testing and on our automation infrastructure. This realization also highlighted the vital role of DevOps skills in our testing. It became clear that integrating DevOps practices into our QA processes was essential in order to address these challenges effectively and to enhance our testing strategies. In this session, we'll discuss core concept of software architecture, monolith and microservices. Moreover, I'll shine some spotlight on the indispensable role of DevOps skills in elevating our testing methodologies, including a special focus on test ops. This session is tailored for developers, team leads, QA professionals, and managers seeking to enhance their quality agenda. You can anticipate practical insights on optimizing testing for both monolithic and microservices architecture. We also unravel the crucial link between software design, testing, and DevOps with a dedicated exploration of desktop principles. Join me as we navigate the vital intersections of QA and automation in the ever-evolving landscapes of software development. Many QAs and even developers often overlook the significance of understanding different software architecture and DevOps infrastructure. This lack of knowledge can profoundly impact our approach to testing, affecting how we design automation infrastructure and implement them. Think of software architecture as the master plan for a building. It's the blueprint that outlines the design and structure of a software application, ensuring it's well organized and operates efficiently to address real-world challenges. Moreover, software architecture determines how various components of the software collaborate and function together, much like arranging rooms in a house. This aspect is crucial because a thoughtfully designed architecture guarantees smooth software operation, ease of maintenance, and scalability to evolving requirements. When software architects design systems, they consider various components like message brokers and databases, all while aiming for simplicity, maintainability, and testability. For instance, choices like monitoring and caching, do we use local storage, in-memory solution, or slower database have significant impacts on performance and data access speed in the application. The architectural choice between real-time data streaming and periodic data collection profoundly affects how we design and implement tests. Real-time system may demand more focus on real-time data validation and concurrency testing, while periodic data system may prioritize data integrity and batch processing validation. Understanding these design choices helps us to prioritize our testing and automation focus for more effective testing. Design patterns are like ready-made solutions for common challenges in software design. They act as clear guidelines to solve these challenges in our code, making our development tasks easier. In automation development, we use specific design patterns like page object, singleton, and factory to organize and maintain our code effectively. The beauty of design pattern is that they establish a common language among developers and encourage the adaptation of best practices. When developers are familiar with these patterns, they don't need to start from scratch when facing a problem. This saves time and ensures that they can implement solutions efficiently. In essence, design patterns are a valuable toolkit for developers, helping them create a more robust and maintainable code, all while reducing the effort needed to find solutions. In simple terms, software architecture is about creating a structured solution to meet system requirements, and the design patterns help to implement them. Let's briefly examine two very common software architecture designs, monolith and microservices. In a monolith setup, the entire system is one big executable application, including the backend application, logic servers, database, and the user interface. Monoliths are known for their simplicity and ease of development, but they can also grow to hundreds of thousands of lines of code, which can make them challenging to maintain and scale. Imagine we have a pizza application in a monolith setup. It might look like this: a bundle application with distinct layers, the UI for ordering pizza, the underlying business logic, and the data access layer for database communication. Now, let's consider it as a very successful pizza place with numerous features and millions of orders on a daily basis. The database could become massive, with numerous tables and many connections, leading to potential problems. This architecture doesn't easily accommodate scalability. Changes that impact the database could result in system downtime. On the positive side, their unified structure simplifies system-wide debugging. However, this very unity can be a double-edged sword, making it challenging to navigate through the codebase, not to mention the amount of time it can take for a developer to clone and build a repository. Maintaining a monolith can be challenging, especially in large-scale systems where the code seems to have a life of its own, growing and evolving endlessly. And agility is often elusive in a monolithic architecture, as instant feedback becomes rare due to the slower processing. For QA teams, one of the most significant challenges is the extended testing and deployment timelines, which can stretch for days or even weeks in sizable organizations. One of the best examples that I have of a long testing process for a monolith is in one of my previous workplaces. We had a small UI issue that needed immediate fixing for a client. After the bug was fixed, it led to two more critical bugs in the pages before and after the pages were fixed. It took us over a week to fix and test everything, and the whole process, including getting it into production, took us a bit over 2 weeks. Now, despite those challenges, a well-constructed and maintained monolith can function effectively, especially when the updates are rare. Testing a monolith requires a strategic approach. Consider the specific features, platform, and time available. Monoliths are tightly integrated, so even minor changes can impact multiple areas. For regression testing, focus on related user flows and components. Collaborate with developers for insights on potential impacts, enhancing your testing coverage. However, it is crucial not to over-test by trying to test the entire system, which can lead to even more delays in delivery. Instead, prioritize high-risk scenarios and areas prone to bugs to ensure effective testing without unnecessary complexities. It is crucial to ensure comprehensive coverage, encompassing both backend and client-side aspects. For instance, when a new feature introduces both a new API call and a new UI representation, it is essential to test both ends, not just one or the other, since in a monolith they are tightly integrated. This includes verifying that the data is correctly stored, retrieved, and updated, especially when multiple components access the same data source concurrently. Effective planning is the road for successful monolith testing. Consider running feature testing on feature branches before merging the code into the release branch. This approach allows for somewhat isolated testing and early bug detection. Perform load and performance testing to ensure the application can handle the expected user load and performance without performance bottlenecks. Assess the application response times and the resource utilization under different loads in order to identify and address any performance issues proactively. Now let's talk about microservices. Microservices are a common software architecture where the system consists of many small independent services that each have a specific functionality, often with its own database. They work together seamlessly, and in this approach, it allows different developers to work on different services simultaneously. Microservices support running multiple instances of the same service concurrently, and they are designed for real-time deployment. Now, from QA perspective, testing microservices is pretty straightforward due to their small independent nature. This simplicity enables efficient and clear test coverage. One significant advantage is that microservices can be independently deployed. This means when we address a bug in one microservices, we won't necessarily need to test other microservices as well, since in many cases it won't affect them. This allows for running a small and fast regression suite, ensuring quick feedback to our customers. Testing microservices introduces complexities due to their distributed nature and the need to function in an unreliable network. This requires testers to investigate advanced root causes for potential failures in network, code, design, and requirement issues. Comprehensive testing of service interactions is necessary to address delays or latency issues that may affect overall system performance, simulating real-world scenarios with varying response times. It is also vital to highlight the importance of comprehensive aggregated logging systems like Kibana or Grafana to monitor and trace service behavior throughout the entire process. Now, let's revisit our successful pizza application compared to microservices. In this diagram, we've divided our pizza service into separate services, each responsible for a specific aspect with its own database. When we compare this microservices diagram to the earlier monolithic pizza application, it is clear that testing them requires a completely different approach due to the various use cases and unique testing process for each. When testing microservices, it is crucial to remember their independence. Testing should include both specific service functionality and end-to-end scenarios. Understanding each service business role is essential for effective testing. A holistic perspective of the architecture helps identify potential vulnerabilities. A well-structured automation framework is vital for scalability and reliability as the product and the number of microservices grow. On top of that, microservices excel in high loads and scalability. Testing should focus on high availability functionality and system behavior under various load and scaling scenarios. Implement automation contract testing to verify API functionality and identify potential issues with service interactions due to changes. Optimize your regression testing by automating all of your testing, resorting to manual testing only for scenarios that can be automated. Another crucial aspect of testing is ensuring that services communicate effectively, even when working with older versions. This ensures backwards compatibility as the system evolves. Now, let's return to my story. As a new QA manager, we were testing a complex microservices and messaging-based system designed to handle high loads with very low latency. Testing this system was a challenge. Initially, we built our automation framework as a monolith, combining UI and backend testing in one repository, which really slowed down the automation development. And as we scaled, the framework became too complicated and we couldn't handle any new microservices. So we refactored it. We separated the UI and the backend testing into different repositories and we adapted the framework to match the product's architecture, allowing us to scale and test new services effectively. We also leverage Docker for automation infrastructure and Kafka for microservices integration testing. Moreover, our automation framework evolved into dynamic microservices documentation, capturing and documenting all actions, events, and APIs through the automation scripts. We talked about software architecture, but I want to emphasize the importance of having DevOps skills in QA. Tools like Docker, Kubernetes, Groovy, Jenkins, pipelines, and Linux are invaluable for automation developers working with both monolith and microservices. Understanding our DevOps infrastructure enables us to implement CI/CD processes seamlessly and to quickly resolve any testing environment issues that may occur. These DevOps tools not only streamline our automation infrastructure, but they also facilitate enhancements, such as Dockerizing them for containerization or utilizing Groovy to define automation pipelines in Jenkins for efficient testing workflows. In some organizations, automation developers are in charge of monitoring and logging. Leveraging these capabilities, they create automation and performance dashboard or environment health check dashboards that prove invaluable to the entire R&D teams. These capabilities collectively fall under the umbrella of TestOps, an approach that applies DevOps principles to software testing processes. TestOps is all about automation and efficiency, with the ultimate goal of improving the quality and speed of our testing efforts. To put it simply, DevOps skills and TestOps principles are essential tools in any automation developer kit. Connecting software architecture understanding with the DevOps architectures ensures efficient and effective testing. We've discussed software architecture, monoliths, microservices, and the need in DevOps skills and how to test each of them. However, it is important to remember that these are the best practices that still should be customized to suit your unique software architecture. To improve your QA team's understanding, assess their knowledge and hold discussions on software architecture about testing approach. Evaluate skill gaps and create a knowledge gap plan. Engage in architectural meetings with developers and infrastructure discussions with DevOps. Involving QA is crucial, as the QA input can uncover bugs early and influence automation framework improvements. Once your team grasps the architecture and services role, they can approach testing with clarity and effectiveness. Thank you for listening. Feel free to reach out.